Thank you so much. I was busy with the other workshop I organized, so thank you so much for inviting me. Typically, for this kind of talk, I kind of collected some topics and give an overview, but I'm going to eventually focus on particular paper our group just published in Science Robotics. So that's for the spectral expansion tree search, and that can be broadly applied to planning and even like optimal control like a method or potential reinforcement learning framework. So we'll see whether you like it or not. Okay. So obviously this is the, let's get rid of this box here. Yeah, this is a cheesy slide. Obviously, there are a lot of advances in machine learning AI. So I'm going to just focus on AlphaGo and AlphaZero, which was regarded as one of the breakthroughs. So the key difference between what we do, obviously not just me and everyone here, and what they achieved is that we have a moving system. We have a dynamical system. We have a dynamical system. It's a continuous dynamics, but also moving in a continuous world. So in the game of Go or this kind of a video game, or some simple manipulation without dynamics, actually it's kind of fixed word, like a grid word, right? You discretize the word and discretize the state. You don't have that kind of luxury that you can have in your dynamical system. So even some of the continuous dynamics done in the video game still is kind of a discretized action space and discretized state space. And also oftentimes when you deploy the robot, it's actually, you have to be able to handle the disturbance, right? And also recently, I'm not going to talk too much about it. Almost every kind of a paper from my group recently is actually has to do with a kind of a failure or fault or disturbance, like heavy disturbance. How are you going to handle that in this era of AI? So to make a more autonomous system robust, right? So the particular technique that was used for AlphaGo and AlphaZero was actually that old technique of Monte Carlo tree search. Monte Carlo means a random, and you take a random actions, but you actually do a tree kind of expansion, right? So basically you put your stone in the Go game, and based on the opponent's selection, you just simulate all the possibilities and then find whether you're winning or not, and you back propagate and update the weight, right? I mean, this is a maybe most famous kind of a recent approach is the upper confidence bound applied to tree, UCT. And then AlphaGo, AlphaZero obviously is very slow, right? Because you have many simulations you need to do, possibilities. So they actually use the deep neural network-based policy and value function, right? That was the innovation, right? So they can actually do that very fast. But that's still not enough because you have basically continuous dynamics. So I'm going to show you that the complexity of when you apply this kind of method to the real-world dynamics. So that's something that we actually sort of try to solve, and then you see whether you agree or not. So obviously, what kind of continuous dynamics we are talking about, and maybe just using this one to talk about our Leonardo robot, so the flying and walking robot that can also do slacklining and also ride a skateboard. Obviously, this kind of robot needs a continuous dynamics, right? And this is actually inherently unstable system, right? It's a kind of walking, kind of embodied pendulum, right? And also you have to handle the unknown wind like this. So obviously, some of the better known work from our group is called the neural flight. And this is actually a tracking control problem. So you have to give a desired trajectory. And then once you give a desired trajectory, the problem is that how can you basically ensure that your drone can follow the desired trajectory pre-given in the presence of this kind of a very heavy wind, time-varying wind. So obviously, the one innovation from this work is that basically nobody knows how to actually train the neural network in real time, doing back propagation and online training in real time. And assuming that you probably need a very deep neural network, and then this is very small drone, and you don't have a computational power. So you cannot really do online back propagation to handle the unknown wind that you didn't really see in your training domain. And that's not the only problem. Even if you are able to carry a supercomputer on your drone, the problem is that you actually use the maybe 365 days of flight data, and then you are ready to rock the world, and you deploy the drone in this kind of very challenging wind conditions, and then realize that, oh, wow, this is a completely different wind profile. And what are you going to do? You're going to abandon all these 365 days of rich data, or you're going to just use the 5 seconds of data you really collected, or how are you going to mix between those two? I think that's still not answered. And we have some partial solution in the sense that we basically trained the neural network to basically differentiate between the previously seen data and the new data, and in the sense of basically time state independent wind profile or wind-based disturbance, because I mean basically wind is completely coming out of nowhere. It's independent of your state, like a position of velocity or whatever orientation you have. So basically, you can just focus on that in the offline training. And what's the best way of updating the certain parameters in real time? Adaptive control, if you know the control theory. And obviously, we use this very old technique, Chung from MIT, is a composite adaptation. So basically, combining the tracking error-based adaptation with some of the least scarce, gradient descent, essentially it's almost like a Kalman filter. You combine that, and obviously you need to guarantee the stability and so on. So that's the end result. So basically, this is kind of almost like you are updating the neural network in real time. In reality, basically, you focus on last layer of your deep neural network, only last layer. And you're perfectly ready to only focus on last layer because that last layer weights are capturing the time-varying parameters of the wind profile that are state independent. The previous layers capture the state dependent. So that's the neural fly. However, this work it still depends on the motion planning. So obviously, I'm also originally a control person and non-linear control. You just focus on control, assuming that the desired motion is just coming from magically somewhere, right? And some of the recent extension is basically applying this kind of neural fly to the fault tolerance system. And it's not just like recovery control. So even though you have a multiple propellers, like conventionally for flying taxis or urban air mobility, if you lose just one or two propellers, if you don't adapt to that change fast, you are going to lose the stability. You're going to have a crash. So here, basically just looking at the internal signals, we can actually find out which propeller actually failed. And in addition to that, we do a real-time adaptation, like a neural fly, so that you can have a guaranteed stability in the presence of this kind of a huge disturbance, basically caused by a failure. So that's a kind of a example of a recent kind of work. But obviously, everyone knows the block diagram, but something really interesting in the robotics world is that although I try to, I'm not the only one, try to send a message, everyone wants to try to compute the online-based something or deep reinforcement learning, and then whatever control signal you compute, you directly send it to the robot without any safety, stability guarantees. I think that's a problem because you might actually have a very good demo with a robotic system. We are able to write a paper. Maybe I'm also one of them. But how can you actually deploy this kind of robot in the real world? How can you actually guarantee this kind of guarantee the stability? I think that's the kind of a part of this workshop's title. So we have a motion planning and like a learning and control, and planning basically means that you compute the desired motion. And my favorite approach is that still using optimized control method. And then you have a real-time adaptation learning. But at the end of the day, you have to guarantee the stability. And at the same time, like a tracking stability means actually also desired the motion with the safety. So that's something that we are specializing in. And I'm going to talk a little bit about that. And so then I'm going to focus on, okay, we have a neural fly-based, learning-based adaptive control that can handle very challenging time-varying wind with a guaranteed stability. But where is the desired motion coming from? So that's the control focus I'm trying to make here. And so that's basically that big block here, computing the desired motion. And obviously, my favorite approach has been using optimal control. So I teach optimal control in Caltech. And essentially, in my opinion, there is a strong connection between reinforcement learning and optimal control. Right? And most fundamental theorem you have in any reinforcement learning is the Bellman equation. That's coming from optimal control. You might not agree with me. So essentially, if you look at this one, you don't sometimes have a very complex constraint that you handle in the optimal control theory, but still you have to have this kind of a discounted real function time integral, and it's very similar to the optimal control problem or your survey Markov decision process, right? So this is the our prior work, and then obviously this is a very common problem in robotics and also aerospace control. You basically, especially multi-agent setting, you have a cost function that are shared by agents, and you have a complex nonlinear dynamics, and equality constraint means that nonlinear dynamics is automatically non-convex, right? And also, oftentimes, some of the interesting constraints with the inequality. Inequality is a giving a problem, not equality, because you cannot just pass the constraints back to the host function, right? Because it's an inequality. Then some of the common inequalities, the collision avoidance. And obviously, we are not the first one, but with a successive linearization from the previous solution, and then also you successively linearize and then convexify the non-convex collision avoidance using hyperplane approximation. This has been successful. And sometimes you can actually have a low-level, high-level decision-making. You actually have multiple loops. So in the sense that maybe you can even compute the desired terminal point so they can actually do shape reconfiguration. So what am I talking about? I'm going to show you the video. And some of the recent work, because it's a robotics conference, it was just published in 2023, a TRO. Okay, so we can also use dynamics, not just perfectly known, because the problem of this method is that you have to know perfect understanding, perfect knowledge of dynamics. But we just talked about the neural fly for tracking control problem, how you handle this uncertainty. Some of the unknown dynamics could be unknown mother, wrongly modeled mother, or it could be actually disturbance coming out of just environment. So here we also use not just a residual deterministic disturbance as a function of a neural network, also you as a stochastic disturbance. So obviously dynamics becomes a stochastic differential equation. And now we have an inequality constraint. What kind of inequality constraint do you have? Input constraint. Your inputs are obviously bounded. And then some of the more common state constraints for robotics world is collision avoidance. So collision avoidance or input constraint or combination of those should be also done in the probability. So that's for the chance constraint. And then so there is a neat way of solving this problem. I'm just going to make a kind of very quick introduction. So saying that for motion planning, we can handle the certain stochastic disturbance coming from the estimation, localization, or mapping. You have certain errors, and you might have an environmental dynamics error. You can capture that even though they are modeled as stochastic. So use a generalized polynomial chaos, and then a distribution robustness, chance constraint approximation, and you can turn all these stochastic dynamics with a chance constraint into deterministic problem using basically set of polynomial equations, and then you apply the SPC. I'm just saying this as an example of some of the optimal control-based motion planning. And obviously, if you didn't know about certain models, and you can actually pass learn the dynamics model, because this kind of approach is as good as the accuracy or robustness of your model you're using, dynamics model or constraint. So if you have an uncertainty in those, you are screwed, because your model your optimal solution might be suboptimal or even not feasible. So you might actually see the collision. So some of the approach we've been taking is that passing some of the learned model in real time to the optimal planning work. But here is still the problem. The big problem is that you still approximate some of the original solution. You need to guess the original solution, and you're linearizing around the solution. So what I'm saying is that this is still fundamentally not truly optimal. And you can get stuck into the local optimal points. So this is finally some of the prior work. You have a large number of agents, although the right-hand side is a TRO paper. That's a probabilistic zone guidance using Markov chain kind of work. So you can handle 1 million agents. You can reshape a large number of agents with the very complex shapes. And then we are solving, that's one example, but going back to the optimal control approach, you can actually have a large number of agents serving simultaneously. You can do that. The problem is that still, even though you have a perfect knowledge of your model, you still have to guess the initial trajectory, and then you still have to somehow have a convexified weird function. And so there are a lot of shortcomings of this kind of approach. And then, so let me actually illustrate that. So we, although Caltech is known for very theoretical work, we formed a team because we've been accumulating some of the research kind of products in the area of motion planning, of control, and like even perception-based localization or mapping and so on. So you think multi-agent collision of free motions is a solved problem. I have a ton of papers doing that. As I actually showed you, I don't think it's solved the problem, because think about this high-speed race car flying at 200 miles per hour, not kilometers per hour. So that's why actually, when I look at the race car dynamics, almost everything is like a flight dynamics actually, because everything is about the aerodynamics, drag, and tire friction, just changing as a function of time, skidding, and so on. It's very complex dynamics, and we are closing the loop. So this is right-hand side video was our recent video from Laguna Seca, the famous track in Monterrey. And then we actually, although we are the latest team just entered this competition, we actually got the best lap speed. Anyway, here is my point. When you actually deal with this kind of complex dynamics, all this kind of discretized work, and then also dynamic programming using some of the known method doesn't scale. You have this curse of dimensionality, and also these uncertainties on known dynamics, you have to handle. So how are you going to get there to solve this problem? So that's kind of a problem we are looking. Again, I'm actually enjoy working on tracking control problem, but this is more like a planning side. So this is that Monte Carlo tree search applied to dynamical systems. So luckily, it was cover of Science Robotics to December 2024. So this is kind of preview. One interesting aspect of this work is that although I talked a lot about Monte Carlo tree search, because Monte Carlo tree search compared to this optimal control method using sequential convex programming and so on, you really depend on the initialized gas. So somehow I have experienced that in our racing car problem. You get stuck, then you just get stuck, and then the car doesn't move because your solution doesn't get to the solution. But if you have this exploration power, like you can have a Monte Carlo tree search, you can actually back up and then recompute the desired trajectory if that's possible. So if you are just using conventional nonlinear programming, some of the MPC kind of work using some solutions like SCP, sequential convex programming, if you just don't do initial gas correctly, whatever linearized dynamics, whatever gas you can do, you just get stuck. So Monte Carlo tree search brings this kind of nice balance between exploitation of the actions or control policies that can really maximize or minimize the control cost cost function, and at the same time, it's kind of explore the different possibilities so that you can actually, it's a higher chance of getting into the higher, better value. So I don't know why the simulation stopped, but this is also quite general in the sense that we have applied that to the drones or going over the thermal wind-based disturbance and also time-varying obstacles. You can see the orange balloons in the previous video. We applied that to track vehicle and even the spacecraft simulator. This is a spacecraft simulator in my lab, basically doing grabbing some uncooperative object and then bring that to the different directions. So controlling some highly kind of under-actuated kind of setting here, because basically what you're controlling is basically tether. So we applied it to many, many different sets of dynamics. So the aim of my talk is to pick your interest so that you can read this paper after my talk. That's my objective. So I'm going to go into the summary of this work. So I think there are twofold. One is that basically how we actually solve this problem of Monte Carlo tree search, that's famous method applied for AlphaGo and AlphaZero, beating human Go champion, discretized world. But how can you apply that to the continuous science in the moving in a continuous? So we have some secret. The second part of the contribution is a detailed convergence optimality proof that can be even used for not just for our algorithm of specialized version of Monte Carlo tree search, but also potentially other versions of variation of Monte Carlo tree search. So that's a detailed optimality method, convergence analysis, that can also guide the design or use of our particular method. So motivation. The quadrilateral moving is unknown world, and you have to observe opportunistically. So previous methods of sequential convex programming and so on might not work because you don't have a perfect knowledge of what's going on. You have to interact. So the simulation-based approach also kind of includes some potential interaction with the environment. So let's see what I have. So this is kind of an example that one of the three examples, and I think this is one of the few papers that have a 3 experimental validation ranging from aerial robotics, spacecraft, even ground robot. So we wanted to really sell this kind of appealing kind of generalization power of this approach. It can apply to your robot, hopefully including humanoid robot and so on. So we have to go into the certain target like white boards and also avoiding this basically wind, basically unknown disturbance while avoiding collision with the orange boards. So that's a problem setting, quite complex. So we solve this problem and it's going to be very difficult to solve using conventional like a method of sequential convex programming and so on. Because I mean, you have to somehow initialize the handcrafted gas, and if you get stuck, you'll get stuck basically. And so we obviously formulate this kind of like optimal control problem. Another way of saying that is a Markov decision process. And then you have this kind of cost function, a very reminiscent of whatever we do in optimal control. But in the spirit of like reinforcement learning, we have a discounting factor as a function of time. By the way, this is what I teach in the Caltech. There are two theories, in my opinion, that are really important in reinforcement learning. One is the Bellman equation that I told you earlier. The second thing is that whatever convergence of this policy iteration, value iteration, you know what? That's essentially exponential stability. That's what you need. That's a control theory of convergence and stability. And that's the only thing you have. Where is that convergence, exponential stability, or contraction mapping coming from? Either gamma of discounting factor, that's smaller than 1, or learning rate, okay? So that's basically one of the techniques that can guarantee certain convergence. Anyway, in terms of complexity, why continuous dynamics and continuous word is difficult? Simply in the discretized word, the complexity is that simply it's exponential, right? So it's basically exponential to the function of a control dimension. So it's exponential function of a control dimension, which means that, I mean, how many control dimensions you have is also the base is 1 over delta U, whatever discretization of your control input. So it's going to be immensely kind of a complex, and then you can actually record the cursive dimension now. And also the delta T discretization step will also make the system more complex. So what we have achieved is that much reduce the branching power factor, basically the width of your tree, and also depth, right? So how you do that? So that's the basically innovation we are basically focused. So how we do that? We actually learn, although we are nonlinear control people, we kind of look into the linear system theory, and there is actually control linear control Gramian matrix, which means that basically if the system is controlled, you can actually have a solution. Basically, point. This is my target point. You can basically get the energy-based optimal solution as an input to reach to that target, and obviously it's a linearized solution. So how can I connect that to the nonlinear dynamics? So that's the question, right? So you can actually have a multiple controllable modes, and then maybe you can rank them, and then basically you can sample only those points that are optimal in the sense of minimizing the input scale, and also basically looking into the mode that are most relevant. So that's the kind of, I mean, basically nodal expansion math. Basically, each tree should be simulated kind of trajectory. And obviously, the different version of our work, we can actually do a local sequential convex programming, including all the constraints. But here, we can also use the input constraints. So you see the clip functions in our pseudocode. Anyway, here, our method is that basically you compute the linear controllability Gramian, and then basically simulate the closed loop with a nonlinear, like a basically controller that can actually track the points very robustly. And then basically this kind of a green banana shape is becoming nonlinear dynamics representation of your small expansion of your basically nodal expansion of your tree branch. Okay. And then of course you simulate with a nonlinear dynamics so that you can actually capture the full nonlinearity. So that's the method. But the reason I am kind of stopping here is that, okay, some of the method you should ensure the stability and so on. So that's basically my specialty. So obviously I'm running out of time. I'm going to go through very fast. If you are already familiar with the Lyapunov function, that's fine. This is a kind of can be viewed as a subset of Lyapunov function, or it can be viewed as a generalization of Lyapunov function. What's that called? Is called the contraction theory. I think we have to read kind of how we teach the nonlinear dynamics, nonlinear control in the world, in the sense that we are obsessed with the stability of a point. But do you care about a point when you develop a robot? Or it's all about the trajectories. So how you actually guarantee the trajectories of multiple trajectories, either converting to the desired trajectory. If it's an estimation theory, what you are doing is that the output of estimator is actually tracking the true motion. That's the objective of your filter or estimator, whether you're running the particle filter or extended karma filter. So this is a concept of extending the original Lyapunov function theory to the stability of increment. So this is for the incremental stability of multiple trajectories. So this is kind of standard stuff. Obviously, sorry about that. I'm running out of time. But very simply put, this is something what you do in the neural drive. You have original dynamics, and then you have either disturbance or learned model. So there will be an error between learned model and then desired model, and that error is encoded as a f true minus f error, which is actually maybe bounded by certain d. And it can be viewed as a disturbance, or it can actually include other disturbance. So it's basically standard stuff in the exponential convergence or exponential stability if you don't want to use the contraction theory. So this is a kind of comparison lemma with a bounded error or bounded disturbance. If you can achieve the exponential stability, you can actually bound the steady state error exponentially fast to the certain constant. So if it's actually cube, people a lot talk about the cube-based MPC and so on, essentially same concept. These trajectories will be converted to the tube, and the tube will have a certain error that's not vanishing. To use that information, you can actually design the better tracking controller. You can feed that information to the motion planner to actually account for some additional errors. And then obviously that's also applied to the discrete time system. Discrete time system or convergence of algorithms where time step from k to k plus 1 will be replaced to iteration in the current step, iteration index w to the w plus 1. So that's famous contraction lemma, mapping lemma used for any convergence of reinforcement learning, but we generalize that to the perturbed system here. Perturbed system. So that's what you see in the convergence proof of assess. I'm going back to the spectral expansion tree search, and then basically error between V star, true unknown optimal value function, and then whatever we can do achieve using spectral expansion will be bounded by this almost like an exponential convergence thing. However, the only downside is that there is an H. So you can see that you could increase the H here, which is basically the size of your tree in terms of time steps. So if you use a receiving horizon control or mother predictive control, that's essentially, oh, I have 10 more minutes. I'm so sorry. I thought we are ending at 4:30. That's why I was going rapidly. Oh gosh. Okay, I'm gonna slow down. So H is the basically number of steps for your tree. So if you are running MPC for each tree branch or H will capture how many time steps. So if you have a larger H, obviously this is gonna get you the small steady error if you don't account this one. However, there's an additional term 1 plus kappa 2 delta t. So unless you select such a small delta t, so that as UH increases, that doesn't blow up. Typically, you have to do the math depending on the problem. So potentially increasing H will be a problem math, okay? So error terms will grow with the H as opposed to actually going exponentially fast, as you can see from the these terms, but it really depends on the problem. So how we actually reduce the dimension? As I said earlier, conventional discretized MCTS, you have to actually discretize your controller space. So even for scalar case, you have if you have only dimension from 0 to 1 or something like that, you have a 1 minus delta U. So if you discretize your input to 0.01, you have 100. And 100 to the power of control dimension. So it's an exponential function of control dimension. We kind of changed that to the linear function, 2 times state dimension. What are basically super great reduction of complexity. So that's the benefit we are getting out of this spectral expansion using linear controllability, Gramian, and then obviously nonlinear correction. The second thing is that obviously D is another important factor, and D is the K is the final time step. So you hit the end of tree, and then maybe you're hitting the target, or you're winning the game, and then that's the time step K, and the K will be divided by the size of delta T, and obviously that's still very large for the conventional problem, but you reduce that now it's going to be K over H, where H means the time step of a horizon of each tree branch. So green is a new method. Red is the old Monte Carlo tree search, just brute force fashion applied to continuous dynamics without sophistication or additional creative ideas. So this is basically making Monte Carlo tree search now applicable to the continuous dynamics, working in a continuous world. So that's basically innovation. So this is a final kind of a convergence. So so basically the reason why we published the paper in Science Robotics is not just because we love science robotics, but you have 100 pages of proof, a mathematical theorem proof. You can just dump that into the supplemental material. So the issue is that maybe people don't read it, but I hope that you can read the paper and maybe let me know whether that proof is correct or not. So in the supplemental material. So in addition to this error term, which is basically either increasing and most likely kind of expanding or decreasing, or most likely expanding as because of this problematic term here, there is an additional term. So L is the number of simulations. So obviously you keep doing in the loop. So as you increase the number of simulation, then obviously you can actually have a better errors. And then basically the gap between the true value function, optimal value function, B star, and whatever estimate you get out of finite, not the full infinity time step or infinity simulation SAS algorithm, some more practical method of stopping somewhere in the final H or final simulation number L, and then also finite D, that's going to be error. So basically error between spectral expansion error and then how fast you are going to converge. So basically the second and third term is effectively convergence. So I'm not going to go into the detail of the proof, but then obviously I have this. So essentially proof is that basically the error between the green banana shape, that's basically nonlinear expansion, and each node, you are going to hit that banana shape, and then how you actually measure the error between the original linear error and the linear term and banana term, and then basically putting all the group kind of terms together to eventually compute the error between the true optimal solution you can hypothetically get, and what's the gap between that or distance between that and our spectral expansion tree search approximation. So what's the value of this theorem? You can use those theorem to guide your design of tree search. How many time steps you need for each tree, or what's the depth of your tree? How many simulations you need to get to have the error close to some value? So obviously this example of UAV flying over the draft, and then this is actually from the experiment, and then whatever we computed as a thing, we can see that the right basically right, the x-axis is basically mode number of this each control-Gramian kind of expansion, and then you see how states are related, and you can see that this becomes a lot kind of a complex when you have a strong thermal that can be used as a basically decision-making parameters for basically spectral expansion. So in terms of a basically final slide, and obviously this is an example, if you see the bottom right one, so the L is the number of simulation, and then H is basically that like a horizon, receding horizon for each edge. So obviously, as I said earlier, as you increase H, it basically kind of converge faster as you increase the number of simulations, right? So it's kind of trade-off. And obviously here, what we have done is that some of the existing method of Monte Carlo tree search, and UD stands for uniform distribution. So you basically, not uniform distribution, uniform discretization of your input, and then obviously it doesn't scale up, and it doesn't really go higher in terms of value estimate, even though you increase the number of estimates. So it's kind of clear that what kind of benefit our method is bringing, but it's a sweep balance. So in this example, the sweep balance happens to be like a H instead of 2000, actually smaller than H, 2000. So H1 1000 actually was the most effective in terms of as simulation number increases, is actually value estimate also increases reasonably fast. So it kind of predict what's the performance, and you can use this kind of theorem to guide your design of Monte Carlo research applied to your dynamic problem. So obviously, as I said earlier, it applies to, this is highly under actual system, because what we are trying to control is the uncooperative, that middle spacecraft is a flat floor, frictionless flat floor, kind of simulating spacecraft dynamics. And obviously is a like a larger dimensional state, because we also measure, include in the model, the multiple distributed spring damper model, mass spring damper model to FEM model to capture the pedal dynamics. So many experimental validation, you can always find how we can actually grab some uncooperative tumbling object and then steer into the right direction. And obviously, this is my favorite approach. This is the DARPA learning introspective control. They added the internal motor errors, and also this is actually finding some very tight corners. I thought that I know how to actually do a motion planning, but it turned out that if it's a very tight corner, or this hyperplane approximation doesn't work. So this actually used the method MCTS, actually beat all the known method of MPPI or some of the MPC method using sequential complex programming, because it actually backs up, or it's more exploration kind of approach, where if you get stuck, you can actually go back and then find a better solution, which you don't really have in a more conventional kind of sequential complex programming. Although you can randomize the certain initial conditions if you wish, but it's still brute force. This is a little bit more systematic. How you incorporate some random on this. Okay, so summary. Similar to AlphaGo and AlphaZero, we use the Monte Carlo research, but in contrast with the AlphaGo and AlphaZero, we are handling robot dynamics deployed in a continuous world. So that's a contribution. I'm sure there are many approaches, but we kind of found a way to systematically abstract the continuous nonlinear dynamics in a continuous world in a more data efficient fashion, and so that we can do large number of like a simulation and you find the motion planning. So that's basically what's the good representation of a continuous physical world. So that was the one small contribution of this paper. So search and learning can improve the performance and interpretability, but basically we need a better representation. Sometimes, actually, it's one of the simulation research. We actually use some of the known intelligent way of doing Monte Carlo research and apply that with a spectral expansion using controllability Gramian and also closed loop with the nonlinear dynamics. And also still it better produce the result. So sometimes actually it's not just the exact search method that's most important, but it's actually how you actually represent the continuous dynamics with a continuous control and action space and then state space. Sometimes that's actually more important. So you never knew how to capability, and then it's a general, we apply to the drone, we apply to the spacecraft, and you applied it to the ground vehicle. What else do you need? Maybe walking robot. Yes, so that's my talk. Thank you so much.